Okay, today we're going to finish the last section or small section of chapter 2. It is called the effect of deductible on claim frequency. So far, we have studied several interesting cases of policy modification. So far, what we have done is policy modification on claim size. Policy modification on X, right? So what we study is when we apply some modifications to the coverage, how would the payment change for the insurance company in either a loss event or a payment event, okay? But today we're going to learn something quite different. That's because the subject is not X, but N. Okay, to understand why it is important to study the impact of deductible on claim frequency, let's look at a very simple example. Let's say I am an actuary of an insurance company and I run a tiny company which probably just sold, let's say, a few policies on auto insurance. Let's say in the past 6 months, I observe, let's say 5 accidents, shall we? We say the first one, let me put. So I observe 5 accidents or 5 claims with losses. Say, let's say X1 is 100, X2 is 200, X3 is 500, X4 is 1000, X5 is 2000. Okay, I simply made up those numbers. But anyway, you can see in this case, N is 5, right? Again, N is the number of claims within a specific risk pool. In my example, probably, let's say there are 10 policies. In the end, 5 of them came back with claims. And we have the claim sizes down here. So it's obvious that if we don't do anything, if we assume there is no modification, N would be 5 for this specific risk pool over the 6 months window. But now let's apply. So now let's change, okay? Let's apply modifications. In particular, I want to apply a deductible because deductible is something we're trying to study today, and it will be the effect of deductible on N. What size do you want to make to be the deductible? Let's say 500. Okay, let's use X. Let's use X tilde to denote the amount. Or let's XL. XL, I think something we use more commonly. So after applying this modification, the first one becomes 0. The second one becomes 0 as well. So is the third one. Okay, and the fourth one becomes 500. The last one becomes 1000. Right. So basically, what I did is to plug each one of them. So I plug each one of them into this modification form, which is the payment in a loss event. So in this case, this is no longer a payment. This is no longer a payment. This is no longer a payment. So essentially, to the insurance company or to me as the chief actuary of this tiny company, there are only 2 claims to me, right? 4 and 5. The first 3, they are 0 to me, right? Of course, they are not 0 to the customers. Customers needs to pay, like the first one needs to pay 100, the second one needs to pay 200, the third one needs to pay 500. But my company doesn't need to pay anything, right? Because after applying deductible, they are 0. So in this case, so if I use NL to denote the number of claims after applying 500 deductible, this is easily 2, right? It's not 5 anymore. So from this simple example, if you do a quick comparison, you see that not only, so what can we conclude? Not only x will change, right? Not only x will change. Okay, so well, n. Using this very simple example, we see that after applying the deductible, the claim severity obviously changes. The claim frequency changes as well. That is the reason why we want to study the effect of deductible. Okay, that's the motivation. So now let's do some series analysis. Right. So now let's say N denotes the claim frequency. Okay, obviously before we apply the deductible, we have a sequence of IID, random variables. Well, Xi is the i's loss. Okay. We don't care about the new loss after applying the deductible. So we don't talk about XL, but we can still put it here. So let's say D greater than 0 is the deductible. So of course, we can introduce this as Xi minus D taking the positive part, okay? But the most important thing is we want to do something different, okay? So let's introduce a new random variable, I is capital I, and with index small I. What we want to model this is, let me give the definition, and you will see the meaning once I write down the definition. Okay, so I give this 0 if xi is less than or equal to d. I assign 1 if xi is greater than d. Because all the xi's are IID, I immediately see that the sequence of these i's are also IID. Okay, not only they are IID, I actually know the distribution, right? They are IID Bernoulli distribution. Okay, what is the meaning of I? Right. So according to this definition, I tells you whether there is a payment in the i's loss event, right? And I equals 1 means it is a loss event. If the value is 0, that means it is only a loss event, but not a payment event, right? So let me use a different color. So this means it is a payment. The i's loss event is also a payment event. Obviously, for this one, it is not a payment event. Okay, I think that is quite obvious, right? That is basically by the definition of this new random variables. Okay, so now what do I want? So now let's introduce this as the define or denote NL as the well, let's use the same notation as the textbook. Textbook use ND. Introduce ND as the claim frequency after the introduction of this deductible. Okay, after we apply this deductible. So this is a new one. Okay, I claim that this new random variable or the new claim frequency can be written in this way. So now take a few seconds to think about this identity. This is an identity. This is not a definition. So this is a result. Can you understand the result behind everything? Or do you are you able to prove this result? And you can simply by deduction, right? Because here ND is the number of payments or number of actual claims after applying deductible. So basically what ND counts, this new ND counts, is the number of payment events after applying deductible D. Okay, so in order for an event to be a payment event, it must be a loss event first, right? So it must be, or they must be, all of them must be loss events first. First, you need something bad to happen, right? And then you need that bad thing to be bad enough. Right? What is bad enough? To be bigger than the deductible. Then there will be a payment from the insurance company to the policyholders, right? So that is why, this ND will only count those with actual losses, right? So if there's no loss from a particular policy, it's not counted. That is why I'm doing this compound summation. So here, what I'm doing is actually compound sum, right? I sum over all the policies that came back with claims or came back with losses, right? And within them, I further pick those with claims or with losses bigger than the deductible, right? So that's why I define zero if there's no payment, because it does not contribute to the number of payment events. Only those bigger than D will be counted towards the number of payment events. So that's the very important result, okay, within that claim. Of course, there's we know the probability of it. So if I want to study the probability generating function of I, okay, I is the genetic random variable which has the same distribution as I. So this will be the expected value of Ti. Okay, I can only take two values, 0 or 1. It is a Bernoulli distribution. When it is 0, the power function is 1. So basically, this is I equals 0 plus T times I equals 1. Okay, now if you look at the definition, when do I get 0? So I get 0 when the CDF of X is less than something, right? So basically, when X is less than something, less than D. So basically from here, I know if I want, I can write it as this plus T times, this is the survival function at D, right? Because I is equal to 1 is the same as X is bigger than D, meaning the probability is exactly the survival at D, okay? But we don't know anything of N, right? We don't know, like, let's just put a notation, call this PNT, okay? Of course, this will be PIT. So what would be the probability generating function of our new random variable ND by the famous result of compound summation, we know the PGF of the sum, it's simply the composite function of both the sum and the term to be summed, okay? So basically this is the best we can do, but we have a very important result. Let's call it the theorem, okay? So suppose my original claim frequency follows a Poisson distribution. So then the mean is lambda, okay? What would be the distribution of P and D? Right? I don't give you the result yet, but let's do a little calculation. So in this case, I know this is e to the power of lambda times t minus 1. Okay, so that is the PGF of power of a Poisson distribution. Okay, let's put some notation. Okay, let's introduce theta as the survival. Okay, then the CDF and D will be 1 minus theta. Okay, so basically I follows a Bernoulli distribution. So our counting random variable will follow a Bernoulli distribution. I believe I use B to denote Bernoulli, or B theta. Okay. So what do we have? Now let's do everything. By the way, with this, we know PIT equals 1 minus theta plus T theta. Okay, and it's a function of T, not theta. Theta is a constant, we know. So my new PGF of ND will be exponential. Let's put EXP lambda. So let's use Pn to replace T, 1 minus theta plus T theta minus 1. Okay, we should obviously simplify. So this one will cancel this one. Okay, I can factor out this theta. So what do we have? So let's introduce lambda. Let's use lambda d, okay, as the original lambda times theta. Okay, with this introduction, what do we have? This is e to the power of lambda d. I tend to write lambda tilde, lambda d times t minus 1. Okay, do a quick comparison to the PGF of a Poisson distribution. What can we conclude? Okay, then we must have this new random variable ND following another Poisson distribution, but with modified mean. Okay, the mean is obviously smaller because this theta is a probability. Again, you know, it's very easy to understand this result. So let me put the result here. Suppose this, then ND will be another Poisson distribution with a new parameter. Well, this parameter equals the previous one times the survival probability at the deductible. Okay. So basically, how do we interpret this result? We can go back to the first example I gave you. So here, let's assume we have a Poisson modeling for n, and we have some distribution for x, which I don't care. All I want to know is, on average, how many claims will be bigger than D, right? I want to know the proportion of it. I don't care about the actual size. That is not our concern here. I only want to know what would be the new count of the payment events, right? And by a quick deduction, I know that this new mean, the mean of my ND will be the previous one times the probability of seeing a claim bigger than the D, right? That explains why in my new, in this very important theorem, the parameter, this parameter is exactly the mean of ND, which is equal to the previous mean times the chance of seeing a claim larger than D. So that's the interpretation of this result. Of course, you can work out more examples, right? So basically, for a few important and you should be able to get an explicit result. This is one of them. You might be able to derive similar result for a different n. N has to be very specific. You cannot get n to be general discrete distribution. Otherwise, the explicit result of ND will not be available. From the textbook, we have an example 2.13 that is on page 78 to 79. So basically, let's assume, well, this question has many sub-questions. So let's first assume x follows an exponential with parameter lambda, lambda equals 1, okay? And the claim frequency is a Poisson. I want to know, so I ask you, what would be the distribution of ND? This is rather simple, right? Because from there, I know the survival function, it is e to negative lambda, lambda is 1, x. And here I want to apply d is a quarter. So the survival at 0.25 is nothing but exponential negative 0.25. You can get a value. I think it's about 0.7788 for an exponential distribution. From there, we know, applying our famous result, the theorem we just proved, we know this ND follows a new Poisson distribution, and the new parameter will be the previous one, which is 1, okay? Well, you can write the formula down first. Okay, this will be 1 times 0.7788, right? So you would know everything from here. If this is just a general lambda, well, you all you need to do is to keep this lambda, right? So let me write it in here. So from here, we know that after you applying this deductible of 25 cents or 25 some unit, the new claim frequency will have a mean which is about 78% of the previous one before applying the deductible, right? So you may consider a different assumption on x. Another one they consider is log normal with mean negative 0.1, variance 1. So the textbook usually put the second parameter to be the variance. So if you want to know the standard deviation, you should take a square root. Of course, it is 1, so it's the same. For this, it will take you a little effort to figure out this. Okay, well, there are many ways you can solve this question. Right? You can say I want x to be greater than this. Okay, I know the distribution of x, but x is a log normal, meaning in order to get normal distribution, I should apply log to x. Okay, then this guy follows a normal distribution with mean negative 0.5 and variance 1. Okay, obviously the next step is to do standardization minus the mean divided by, okay, standard deviation. Although, it's the same as 1, but I write it here just to make sure. Of course, I need to apply log on this side as well. Okay, if you want, you can write this as negative log of 4 if you want. Okay, so negative log of 4 plus 0.1 divided by 1, so it's 1. Okay, from here, this is a standard normal, right? This follows a normal distribution with 0, 1. So you have the table. Well, at least you can use R or MATLAB or Maple, Mathematica. Any software will be able to quickly give you this result, right? The textbook also asks you something different. Okay, still X will be either exponential or a log normal, but now your N is not Poisson. Poisson is always easy. Now what you have is negative binomial with R and theta. So this is slightly more complicated because in this case, we need to revisit our proofs previously, and we need to basically do everything one more time, meaning I need to write down the PGF of n, which will be a big bracket, 1 divided by 1 minus beta times t minus 1, another bracket, take to the power of r. Okay, from here, what do we know? We want to, of course, from the equation, we have this. So beta is 1 minus theta divided by theta. Okay, so it is a short notation to make it look better in the probability generating function. Okay, so with what you have, you can still write down the PGF of I if you want, but the question asks you found the distribution of the claim frequency with the deductible. Okay, now we need to, what we need to do is, we know this is still the same. I shouldn't use theta anymore because we have the theta from the second parameter. So let's keep the CDF and survival function that won't cause us any confusion in notation. Okay, so the PGF of ND will be, well, put everything in. It will be 1 minus beta. Okay, so t minus 1, I will use this to replace t. So it will become sxd times t minus sxd. Okay, so the 1 divided by this and raise the power to r. Okay, it looks very, very close. So what I mean is, if you do a quick comparison, they are in the same functional form, but not exactly the same, right? Because here the factor in front of t is 1, but here it's obviously not, right? So what can we do? So obviously we are trying to work out the same formula, right? So the thing is, we need to do something to make this one going backwards. So basically, we want it to be back to what we have. So we will need to in this problem, we will need to R will be the same, right? Because if we do a comparison, R will be the same. But the thing is, what would be the new beta from this particular question, right? From the new beta, we can get the new theta of it. What we claim is this will be the same as our factor it out. So basically what you do is you take it out, and it will go back to the original form of what you have. So we can take out of everything we have. By the way, I think this is not FD. This is my mistake. I mean fx, so I can write it as 1 minus x, 1 minus x s. So here it will be x. So that's why when I take it out, what you have will be d minus, not d, t minus 1 inside. So the inside part will be t minus 1, and the whole term divided by 1. So what would be the new beta, right? We immediately see this would be your new beta, right? If you want, you can put beta star to denote this, right? And from beta, we can go backwards to get the new theta star. So that will be 1 divided by 1 plus my beta. Okay, which you can obviously calculate. So now what would be the distribution? Finally, let's conclude. What would be the, finally, let's conclude. This will be another negative binomial. The first parameter remains the same. The second one will be much different, and it is given in this form. Okay, I think I should end here for the last part of chapter 2.